Hello, welcome to the channel. Let's continue with the KSET January 2024 question paper. So in the previous videos, we have already discussed the inorganic part as well as interdisciplinary part. First 40 questions have been covered. Now in this video, we are starting with organic. So starting from question number 71 up to 130 questions, they are from organic chemistry. So in this particular video, first 15 questions we will be discussing in detail. Let's start the video. Before going to the questions, if you are interested in chapter wise as well as topic wise sorted KSET previous year questions, you can refer to these books, KSET in chemical sciences, inorganic chemistry as well as in physical chemistry, and you can just contact the given number via WhatsApp to get your copies. Let's begin with the question. First question, very simple one. What is the Iupac name of the following compound? I should say this is +1, +2 level question, or even high school students can try to answer this question. Such a simple question it is. So the important thing is that we should know how to number the carbon chain. Functional group CHO, it is aldehyde, and functional group it should take the least probable number. So therefore numbering it starts from this end 1, 2, 3, 4, and at second position we have CH3 group, methyl substitution. So therefore straight away the answer it will be 2-methyl butanol. Very simple. You can just look at the other options. So 3-methyl butanol, if you number it in wrong way, say 1, 2, 3, if you go in this way, then you can get this as the answer, but the correct way of numbering it is this itself. So therefore 2-methyl butanol, that is the correct answer for this. Again, second question, it is also Iupac name itself, a diketone it has been given. Very simple. So in fact in this case numbering doesn't matter because the molecule is symmetric, 1, 2, 3, 4 or 1, 2, 3, 4 doesn't matter. So let's number it as 1, 2, 3, 4. Now we find that at second position as well as third position carbonyl functionality, ketone functionality it is there. So therefore this should be a diketone, dione. So at 2 and 3 position it is that. So therefore the correct name it will be 4 carbon atoms and 2 and third position ketone. So therefore it will be butane 2,3 dione. Option C is the correct answer for this. Third question, 73rd question in the question paper. Very simple one again. Which of the following compounds will show geometrical isomerism? Just we should know what are the conditions for geometrical isomerism. Conditions of geometrical isomerism, if we see, first thing, restriction of free rotation about the carbon-carbon single bond or carbon-carbon bond, that should be possible. So that is possible when carbon-carbon double bond is inserted, and even if ring is there, that ring also sometimes it can give this restriction. Just now if you look at these options, everywhere you can find the double bond, so therefore restricted rotation it is there, and this condition it is followed everywhere. Second thing is that different substituent groups on both the carbon atoms. So if you look at here, the carbon atom, both carbon atoms, they should have different groups attached, CH3HS. These two groups they are different, so it is possible. Here also these two groups they are different, it is possible. But if you look at the other options, see here, these two groups on one of the carbon atom, both the groups they are hydrogens. In such scenario, geometrical isomerism or cis trans isomerism it will not be possible. Even if you expand it here, CH2 it will be just like this. So therefore both groups they are hydrogens, geometrical isomerism it will not be possible. Here also same thing, both groups they are hydrogens, or on one carbon atom same groups they are present. So therefore geometrical isomerism it should be possible only in this particular option, option A. In fact this particular isomer whatever they have given, it is cis, or in terms of E and Z nomenclature, so this will be Z. The other form, E form or trans form, that will be possible for this. Cis trans isomerism it is possible, geometrical isomerism in option A. Option A is the answer for the question. Let's move on to the next question. Interesting one. So they have given a cyclohexane molecule with 3 substitutions, and they have asked how many alkyl substituents will be axial in the lowest energy conformation. So first we shall see what is the lowest energy conformation, and then we can decide how many axial groups will be present in that. So for that we should have the thorough knowledge of conformations of cyclohexane and converting the cyclohexane conformations from one to other form. So now first I'll rewrite this in a different way. So here the care that has to be taken is that, so this solid wedge, it indicates that the group methyl group, it is above the average plane of this cyclohexane ring. So that's how methyl group at first position. So this carbon atom, it has been considered to be first, and the numbering it has been done in this way. So on first carbon atom, methyl group, it is above. So second group, if you look at, so second position, it is ethyl group. So here you can see that it is below, it is shown below. So therefore here also I take it below. Then third, no substitutions. And on fourth carbon atom, if you number it like this, so numbering I can just indicate it here also. 1, 2, 3, 4, 5 and 6. So now on fourth carbon atom, isopropyl substitution, so that is below the ring, so that has been indicated here. So once I convert this, now I can convert this easily to the cyclohexane form. So if I convert this to cyclohexane form, cyclohexane, you will be knowing that it will be having, say, chair conformer, stable conformer with axial and equatorial substitutions. Very important thing. So where you send the substituents axial and where you send the substituents to equatorial position. So especially when the forms are given like this. So how we can do that easily, that we shall see now. See now here, one thing what we can understand is, so this group methyl which is above, so here also I send it above, CH3 on first carbon atom. So between these two, when you are doing this kind of conversion, so it is possible to do that by remembering it like relationships, axial, equatorial relationships. That is one way, but the easiest way from this form to this form, see what I have done is, this position it is above here, and here between these two positions, this is actually called as axial, this is equatorial. So this position I just call it as above, and this position I call it as below. So here substitution above, so same thing I have done here. So now if I come to the second position I see that substitution it is below. Same thing I'll just adopt here. So this side, now second position, here this position I can call it as above, this position I can call it as below. So like below means it should be here, CH2, CH3. Now further if I go, on fourth position it is below, so again same thing, above, below, so I should include substitution here. So it is this, if you consider it as carbon atom, say further CH3 and CH3. Now the question is about the lowest energy conformation. If you have some basic idea of cyclohexane conformations, you will be knowing that axial positions with these alkyl substitutions, it is not favored. It is because of 1,3 diaxial interactions and some other interactions, kind of interactions called as Gauche-Butane interactions. So this is not preferred. So the molecule, it can go to the other form, ring flip can happen. After ring flip, this axial groups whichever are present, they can come to equatorial position. That is possible, right? So seriously speaking, if I go for ring flip, thus this one it should come here, to it should go here, and so on. But I'm just not doing that. Just for the sake of understanding, I just want to keep the numbering as it is. So just I'll change the position of substitutions. So CH3 axial to equatorial, CH to CH3, now it is again axial to equatorial, means it should come here, and this one also axial to equatorial, means this substitution I just draw it like this, so it should come here, right? So now this will be the most stable conformer because all the alkyl substitutions, they are present in axial position. So now for this, either this is possible or this is possible in its most stable conformation if we consider the chair conformation. So now in this one, all the three they are axial, here all the three they are equatorial, and this will be more stable. And now if you count the alkyl substituents which are in axial position, actually they are 0. But none of the given answer it matches with that. The given answer, I should just mark up the given answer, it was B, but I don't know why this question it has not been challenged. The correct answer according to me for this question, it should have been 0, which is not given. So because of that grace marks it was expected, somehow even grace marks it has not been given, right? So this conversions understanding, it is very important, and you can just cross check this particular example in any of the book, and I'm quite sure that it will be this itself which is more stable conformation, and I don't find any possibility where just one substitution coming to the axial in the most stable conformation. Next question, again very simple question from aromaticity. Which of the following is not aromatic? We should just know the conditions for aromaticity. Conditions for aromaticity, if you talk about, The molecule, it should be cyclic. If you look at the molecules, all these molecules, you can find them that they are cyclic. Then the molecule, it should be planar. Of course, like if the ring is larger, then in that case we can think of non-planarity. But all these, they are planar rings. And continuous delocalization pi electrons. If continuous sp2 carbon atoms they are available, that will be possible. That is there in all the three cases. You can just verify that. So last condition, or which is known as Huckel's rule, this if you come across, so what this says is that for a molecule to be aromatic, it should have 4n plus 2 pi electrons. So that means n, you can just substitute it as 0, 1, 2, 3 and so on. So if you do that, you can find that if the pi electron number, it is 2, 6, 10, 14 and so on, then the molecule, it can be aromatic. Now if you count the number of pi electrons in each the case, so here only one double bond, and that's how it's 2 pi electrons, so it should be aromatic. Here if you look at 2 pi bonds, 4 pi electrons, so if it is 4 pi electrons, the molecule, it cannot be aromatic. Right, so the question is which is not aromatic. So this is one of the options. You can just look at the other options also. So here with plus charge, only 3 pi bonds, it is 6 pi electrons. Here 2 pi bonds and 1 negative charge. This indicates one pair of electron which is also participating in delocalization. So that's how totally 6 pi electrons. Both these systems, they are aromatic. Even A, it is cyclopropenium cation, so that is also aromatic. Option B, which is they have asked, which is not aromatic, so this should be the answer. In fact, with 4 pi electrons, it will be an anti-aromatic system. Somehow not aromatic, it means like even anti-aromatic, we can conclude it in this itself. So therefore option B, it should be the answer for this. 76th question. Which one of the following compounds on further substitution can yield theoretically only one substitution product? This is interesting question. So now, first thing we should know, two different types of substitutions we can find, nitro groups, and in only one case you have methyl. In all other molecules it is nitro group. So the directing ability of these groups you should know. Nitro group, if you consider, actually it is a ring deactivator, so it makes the ring slightly lesser reactive towards electrophilic substitution. Of course, this is just for information. The information that we need to solve this question, it is here. It is meta-directing group. Nitro group, it is meta-directing group. The methyl group, it is activating, and it is ortho and para director. Now, with this information, just with the exam logic, so sometimes there will be a logic which is applicable only in exams. Seriously speaking, to this question, that exam logic, it is very much essential. Otherwise, even for this question, I should say grace marks, it should have been avoided. But with the exam logic, how we can solve this question, that we shall see. See, first thing, so nitro group, I said it is meta-directing. So therefore, meta-direction means like this position, it is meta with respect to nitro group. So substitution, further substitution, it is possible here. Further substitution, it is possible here. And with respect to this methyl group, if you talk about, this is ortho and para director. Para position, it is blocked already. So therefore, these two positions, they are favored by methyl. So like substitution, it is possible here, or substitution, it is possible here also, further substitution. So if you go with the second option, so nitro group, again, meta with respect to that is this group, it is this position, and meta with respect to this nitro group, it is this position. Substitution, it should be possible at both the positions. So therefore, according to this particular question, the logic that they have asked, so two things, or substitution, it should be possible at two positions, or these two positions. Now further, if you go to the option C, so here with respect to this nitro group, meta, it is ortho meta here, and with respect to this nitro group, it is this position. So therefore, according to the question, only substitution, it is possible here, right? So it should theoretically yield only one product. That's what they are expecting. Further, if you just extend the logic here, nitro group, meta means for this nitro group, two meta positions, for this nitro group, two more meta positions. So therefore, it should be say like here and here, according to this one, this group, and here, it should be possible according to this group. Right, so according to the question, so option C, it should have been the correct answer. And yes, it is given as the correct answer. But if you think, if you are just considering one more substitution for this molecule or for any molecule for that matter, say one of the group, E group, it substitutes here, right? So what we are getting is that, say, if I just number this as 1, 2, 3, and 4, so you have substitutions at 1, 2, and 4th position, right? So if the substitution it happens at this position, in that case also 1, 2 and 4th position. So whether the substitution it is taking place here or here doesn't matter. The final product what we are getting, that will be actually same, right? So same logic it can be applied here, same logic it can be applied here. So seriously speaking, according to me, it is not that good question, but as per the exam logic, option C it is the answer. And sometimes we should just follow the exam logic that is there in each and every exam, right? Maybe further, if we think of isotopic substitution and all, okay, in that case, say if this carbon atom is isotopically substituted, in such scenario, okay, only one particular product it is possible that can be substantiated. Otherwise, it is a bit difficult, because if you consider just single substitution, everywhere you will get the same product itself. So like the substitution, it may happen, it may look it is happening at different position, but the final product it will be just the same. Fine, let's move on to the next question. Again about the stability, and again with this question, whatever answer they have given, the final answer, so I'm not completely agreeing with that. So 3 cations they have given, and they have asked which of they have asked the stability order of these carbocations. One thing is very sure, that this is aromatic. Just now we have seen that this will be aromatic. It's following all the conditions. So therefore aromatic carbocation, it should be more stable, no doubt about that. So either the answer it should be A or C. So the next thing it comes now, between these two, this is cyclopentane cation or cyclopentelium cation, this is cyclohexene cation, hexylium cation. So between these two, which is more stable, right? So according to the literature, when the ring size is larger, it tends to stabilize the carbocations due to its ability to relieve the strain, and even more hyperconjugations will be possible. Because of all those reasons, this is considered to be, generally I'm speaking, so like larger the size, that is considered to be more stable. So that logic it should be applied here also, and as per that, the correct answer it should have been, so option C, because one is more stable, cyclohexylium it is more stable, and then least stable it is this. But somehow the given answer it is A. Why they have given this answer, or if there is any other explanation in which this stability, cyclopentelium cation, it is said to be more stable than cyclohexylium, in that case this can be considered as answer. If you know any such logic, you can just let me know that in comment. Otherwise, I would go with option C as the correct answer for this question. Let's move on to the next question. This is also simple question. It's about the stability of carbon ions. So 3 carbon ions they have given, and they have asked the stability order. First thing is that if you look at this one, this is not an aromatic system. So therefore, even if nitro group is present, delocalization of this minus charge it will not be possible. In these two, because these are aromatic systems, so delocalization it will be possible. So when you compare these two, additional nitro group is present. This additional nitro group, it can contribute, or it can give one more additional resonance structure. So that's how between these two, this should be more stable. So how the resonating structure is possible because of this nitro group, additional resonating structure, or how the charge it can be delocalized up to this nitro group, that is shown here. But if you write the resonating structures, you just find that this particular structure you find extra in this. So that's how this is more stable. So most among these 3. So therefore option C, 2 is most stable. Next comes this 1, and next comes this 3. That is the correct answer. And option C, this is the correct answer for the question. Next question. Again, a simple one. If you know something about SNI mechanism, easily this question it can be answered. Whenever this thionyl chloride SOCl2 it is used, or whenever it is present in the molecule, there is possibility of SNI mechanism. So in fact, alcohols, when they are treated with thionyl chloride, first it will form this particular sulfonyl chloride of the alcohol, and now they have started from that, and then this will give you the product like this. So this SOCl to the Cl which is present inside the molecule, that itself will attack the R group, and see this bond it will be cut, and SO2 it will be liberated. This particular kind of mechanism it is called as SNI mechanism, right? So a very important thing about SNI mechanism, about substitution, nucleophilic, unimolecular and bimolecular, SN1 and SN2, we know SN1 its stereochemistry always it results in racemization, whereas SN2 we say that it will result in inversion. But in the case of SNI that has been shown here, so this bond, this particular bond, it is above the plane now. Even after this Cl attack, this Cl bond, it is above the plane itself. So that means SNI, it results in retention of configuration. That is the importance of SNI. So straight away SNI, option C, it is the correct answer for this. Again, 80th question, it's a general itself about substitution mechanisms. So a substrate they have given XCH2Z. So here we should consider that X, it is the leaving group, and Z, it is the other group which is present in the molecule. So now when Z is dash, the rate of SN1 reaction, it increases. So first we should know, so like how SN1 reaction happens and when we can expect the rate of SN1 reaction to be increased. In SN1 mechanism, first step, it will be ionization. This leaving group X, it will leave the molecule as X minus, forming carbocation. Whenever this carbocation stability is more, or in other words, if this Z group, it is stabilizing the carbocation, in such case, the SN1 reaction rate, it will be more. So now we should just look for that particular Z group which can stabilize this carbocation. So among the 4 groups that they have given here, so this group RO group, it can stabilize this carbocation. All other groups B, C and D, so they will be destabilizing this carbocation. So that's how they will not accelerate SN1 reaction. So if the Z group, it is electron donating, in such case we can expect it to be stabilized or this carbocation being stabilized. If it is electron withdrawing by minus R effect, in such scenario it will destabilize. So therefore RCO, CN and HCO, they will destabilize carbocation and they will not help SN1 mechanism, whereas RO, it stabilizes the carbocation by plus R effect. So like oxygen lone pairs, they can be donated and this carbocation, it can be stabilized with the double bond formation here, and oxonium ion will be formed with a plus charge over this oxygen atom. So that's how the option A, RO group, so that will increase or that will accelerate the SN1 mechanism in this particular molecule. Predict the correct intermediate in the following reaction. So NH2 minus they have given. So NH2 minus, it is a strong base, so that will abstract a proton. So if you know benzene mechanism, otherwise also we can just make it out that they have given benzene, so this follows simply benzene mechanism. So the most acidic proton, so proton which is between these 2 electronegative groups, this will be most acidic one, so that will be removed first, and then one of the group, it will leave, right? So it has been shown here. So this H plus, it is removed, and then what we can expect is that, so this migrate here, this pair of electrons, they'll migrate here, and this Cl, it can go out. The other possibility is that this pair of electron, it can migrate here, and this Br, it can be removed. But if you look at the options, in all the 3, they have retained Br, so therefore it should be possible that this Cl, it should be the leaving group. This is so here we cannot think that Br should leave first and Cl should leave next. This is not substitution nucleophilic mechanism. This is not SN kind of mechanism. This is even CB mechanism. So therefore Cl group, it behaves as sluggish and that leaves the molecule most, and this will be formed. So that's how option B, very simple one, option B, it can be considered to be correct answer for this. 82nd question, again very simple question. So which of the following reaction it can generate carbene intermediate, they have asked. So of course both the reactions they have given, and if you have some basic idea, you can easily say that yes, in both the cases carbene, CCl2 dichlorocarbene, it has been formed, and so this one, it is very well known step. So like if you know in which reaction you come across this step, you can just let me know that in comment. So this is in one of the named reaction, it is first step, very important step. So here also same thing, you can expect carbene formation, you can expect. So when it is heated, sodium salt of carboxylate, so this minus charge, it moves here, and this bond, it goes here. So just this CCl3 I have expanded just to show you the formation of dichlorocarbene. So in this case also dichlorocarbene, it is possible, and carbon dioxide and NaCl, they will be the other products. So therefore in both the cases, it is possible that option C, this should be the correct answer for this question. Option C is the answer. That is, in both the cases we have the formation of carbene. It is of course dichlorocarbene. 83rd question. Again, very simple, very well-known reaction, Pinacol-Pinacolone rearrangement, but it's not directly Pinacol, but it is a asymmetric Pinacol molecule they have given. So now we shall briefly see the mechanism. It's not complete one, brief mechanism, and based on that how we can get the product that we shall see. So first thing is that in acidic medium, one of this OH group, it is protonated to produce the carbocation. The method or the protonation of this OH group, it happens because in the next step the water molecule whichever is removed, it will produce carbocation. So now that particular hydroxyl group will be protonated where carbocation stability is more. So like protonation, here also it is possible, here also it is possible. So here we have considered, because when water molecule it is removed, it is shown here. So when protonation happens, this will become OH2, and like this bond it migrates and water molecule it is removed, plus charge you will get here. This carbocation, it's tertiary. Of course, even if it happens here, tertiary carbocation itself will get, but the additional stability it is due to this pH. So this becomes benzylic like of carbocation. That's how this can be additionally stabilized. So therefore, carbocation formation it happens here itself. So in this particular reaction or in this particular type of reactions, the next step it will be rearrangement. Always from the neighboring carbon, one of the group it will migrate. So here also, no confusion, because like both the groups they are methyl itself. So if these groups they were different, in that case we may have to follow the migrating aptitude. So now no question of that. So one of the methyl group, any methyl group you can consider, it will migrate here. And the driving force, actually I have not shown it here. Driving force for this is that formation of say plus charge you will get over this oxygen, and that is the driving force of for the transfer. That step I have not shown directly. So like one of the group it migrates here, so one of the group it migrates, and the plus charge you can consider it will come here, and water molecule it will take up this proton, and this plus charge it will be neutralized by the formation of double bond. So option C, it is the correct answer for this. This is also a simple question itself. 84th question, Fry's rearrangement of phenyl propionate. Fry's rearrangement, if you know, straight away from that knowledge you can answer that in Fry's rearrangement both ortho as well as para hydroxy, or say ortho and para products are possible. Just I'll show you the reaction. This is the phenyl ester. So this R group, you can just think that it is a propionate part here. And now when it is treated with Lewis acid in acidic medium like HCl, so what we can get is either ortho product or para product. Both are possible. So like why both are possible, that we can understand from mechanism. So let's not go into the details of mechanism. I'll just give you the mechanism. The correct answer for this, it is this option D, right? The mechanism it is shown here. So important thing, you can just pause the video and you can note the things here. So the thing is, in the first step, this acylium carbocation it will be formed. So in the second step, when this ring it attacks acylium carbocation, say this lone pair it comes here, either it can happen with the ortho position, or this delocalization it can continue, and it can happen via para position also, which is not shown here, right? So that's how both possibilities are there. Last question in this particular video, again very simple reaction. So it's about named reaction. So just if you know that this is Wittig reagent, PH3P CH2, it's Wittig reagent which can be treated with carbonyl compounds like ketones to get this compound, you can easily answer that this is option C, right? So it's actually Wittig reaction. So in Wittig reaction, essentially what happens, it's not mechanistic point of view, simple prediction of the product, you can do it like this. Wittig reagent, it introduces this CH2 group here, and this O group it will be transferred here, and the triphenyl phosphine oxide, that will be the other product. One particular example it has been given here for Wittig reaction. So in Wittig reaction, this is the reagent used, and that's how option C is the answer. Just for understanding sake, we can look at the other reactions, what the reactions are. First one, it is Chichi-Babin reaction. It is the reaction of pyridine. So when it is treated with NaNH2, so like NH2 group it will be substituted here, that is known as Chichi-Babin reaction. Then Fry's rearrangement, just now we have seen, so phenyl esters they are undergo rearrangement reactions. That will be called as Fry's rearrangement. And the last one, Wills-Meyer-Hack reaction. So Wills-Meyer-Hack reaction, it is actually introduction of CHO group. So confusion it is possible between this Wills-Meyer-Hack and Wittig, because like If you are confused with this in Wittig reaction, it is carried out in DMF solvent and POCl3. This is the reagent, and it will introduce a formyl group whenever a electron donating group it is present on the ring. So this is Wittig reaction. So with that, first 15 questions in organic chemistry we have covered. So in the next video, we shall take up the remaining questions from organic chemistry of KSET-Jan 2024 paper. Thank you for watching this video. If you are new to channel, you can just subscribe to this channel. You can share this video with your friends so that even they are benefited. So you can know your opinions through comment. Thank you for watching this video. Thank you again.